Swayam Prabha. Digital India. Educated India.
Dear students, I take this opportunity to introduce you or welcome you to this course on mineralogy, which is being offered from the Department of Geology and Geophysics, IIT Kharagpur. And the course will be taken by me. I am Shantanu Kumar Bhaumik and my colleague Professor Sujoy Kanti Ghosh. And before I go into this topic, so let us give you the course structure. This mineralogy course will be is subdivided into three parts here: crystallography, optical mineralogy and mineralogy. So, I shall take the first two components, crystallography and optical mineralogy. Mineralogy will be taken by Professor S.K. Ghosh. Now, if you see these first two components here, what we are covering here in crystallography, we will be essentially covering the concept of symmetry, the 32 crystal classes, the 2D and 3D lattices here, and we will be also talking about how to name the phases, how to name a direction, concepts of Miller indices, crystal zone axis, and also the crystal forms. I will also give you the concept of stereographic projection here. In optical mineralogy, we will learn the concept of polarized light and the refractive index of minerals, and I will also tell you the significance of Baker line test, optical indicatrix, the concept of double refraction, birefringence, optic axis, principal section of indicatrix, and the concept of uniaxial and biaxial minerals, what is the interference color of minerals, how Michael-Levy chart can be used to find out what is the order of interference color, and we will also tell you about the significance of uniaxial and biaxial interference figures and how they can be used to determine the optic sign. In mineralogy, we will talk about the basic concepts here and particularly the crystal structures and also the silicate crystal structure, the subdivisions, Pauling's rules, and also polymorphism, and also the energetics of mineral stability, the concept of solid solution, X solutions, ordering, twinning, crystal growth and defects, and also we will try to give you how to normalize mineral oxide data to cations. And we will also be talking about the different types of silicates, particularly the nesosilicate, cyclosilicate, sorosilicate, phyllosilicate, ionosilicates, tetrasilicates, and we will be discussing in some details some critical minerals under this silicate structures here. Now, what are the reference textbooks that we will be using in this particular course here? For crystallography and crystal chemistry, I will be following a very old book by F. D. Bloss, that is Introduction to Mineralogy and crystallography and crystal chemistry, and also we will also be using a book by William D. Nesi, Introduction to Mineralogy. And for optical crystallography, we will be using the book by Wallström, and there are also other books which are written here, which can be consulted for this particular course here. Now, let us have a look at this geographic map of India here. So, you can find out that this is the Himalayan mountain chain here, starting from Nanga Parbat in the northwest, and as passes through the Namche Barwa in here, and this is a mountain belt. You know that this is essentially composed of rocks, and some of these has reached very great peaks here. And what are the rocks that are found here? So, there are three varieties of rocks we know. One is metamorphic rock, there is igneous rock, and sedimentary rocks here. So, essentially if you see here, if you collect rocks here, you will find out certain rocks where you will find out the pink colored minerals which are garnet here, and there are other minerals here, slightly elongated mineral, as you see here, these are kyanite here. So, these are kyanite schist here, and the other type of mineral you will be also be seeing here, there are staurolite crystals here, and also you have muscovite white colored part, these are staurolite muscovite schist. So, these are rocks which are metamorphic rocks and are composed of some diagnostic minerals like garnet, kyanite, staurolite here. If you see the rivers which are coming down from the Himalayas, for example, the Ganges as you flow here, you will find out that in the upper reaches here as it erodes the Himalayan mountain chain here is composed of bouldery masses here, and as it progressively the velocity decreases here, these rocks cannot be transported in the river stream, they are deposited, and you have this kind of outlines of individual fragments of rocks and minerals you can find out here. These are sedimentary rocks here. And if you are in Nagpur or in the western part of the Maharashtra, you know that there is a dark colored rock, we call it as basalt, and this is this very fine grained rock composed of clinopyroxene and plagioclase here. So, this is an igneous rock here. So, in these three types of rocks, you have essentially minerals here. So, mineralogy is essentially literally means the study of minerals here. So, what are minerals? Minerals are naturally occurring solid with a definite, but generally not fixed chemical composition, and they have a very highly ordered atomic arrangement, generally formed by inorganic processes here. So, what are the important part? Minerals are naturally occurring. So, the process has to be naturally occurring. Synthetically produced solid materials cannot be called minerals, and they have a definite composition here. They are not fixed, I will explain to this, and they have a very highly ordered atomic arrangement, and they are formed by inorganic processes here. I give you two examples here. One is on this here, we call it as olivine, and you see this chemical composition here. There are two cations of Mg and Fe together, one cation of silicon and 4 anions of oxygen. So, you have a grouping here that is SiO4. So, in this, if you have to have an olivine, you have to have an SiO4 grouping here, that is fixed composition, and you have to have two divalent cations here. In the octahedral side, you have to have two cations together, but importantly there will be substitution between magnesium and iron, so that you have compositional variation in olivine. In the same way, if you see garnet, there are three types of crystallographic sites here. This one is the tetrahedral site, which is occupied by silicon, they are 3 in number, and you have octahedrally coordinated sites, which are trivalent cations, aluminum and ferric is there. So, they are together, they are 2 in number, and you have cubic coordination here, where you can have divalent cations like magnesium, iron, manganese and calcium. So, depending on the type of garnet, the important thing here is that you have to have this grouping of Si3O12, and depending on aluminum and ferric, either it has to be aluminum 2 or ferric 2, but importantly you have significant amount of substitution of between Mg, divalent iron, manganese and calcium here. So, what you have here is that you have a fixed chemical composition in a particular grouping, the silicate grouping that we have, but you have substitution among the cations, which will give rise to compositional variation here. So, essentially the mineralogy is the study of the chemistry, atomic structure, physical properties and genesis of minerals here. And I will try to give you some idea about some general features of minerals. There are around 3000 minerals that have been identified. Most are compounds, specifically they are silicate groups of minerals. So, composed of silicon and oxygen. So, SiO4 grouping or SiO4 tetrahedra, they are shared among each other to form different varieties of silicate structures here. Other important groups are oxides like spinel group of minerals, carbonate like calcite, sulfide like say pyridite and phosphate say like apatite. A few are native elements made of only one element, such as sulfur, gold, copper and graphite. Now, let us give you a perspective of the subfields of mineralogy here. There are different mineralogy can be studied under different subfields. So, you can have descriptive mineralogy. So, essentially in which we document physical properties of minerals. I will give you some idea about what kind of physical properties that we use. We also study optical mineralogy. There are optical properties of minerals are studied in this field. There are crystal chemistry. So, where the relationship of chemical composition to atomic structure are studied. We will also study crystallography. is a relationship of crystal symmetry and form to atomic structure. So, this is the topic we will start, and we will also have a subfield of how the minerals are formed under mineral genesis here. So, we interpret the geological setting in which a mineral forms from its physical, chemical and structural attributes and its associated minerals here. Now, what is the fundamental position of mineralogy to all other earth science disciplines? The first is the petrology. So, in petrology, how mineralogy finds its place? This petrology is a study of the origin of rocks. This is largely determined by evaluating the structure, texture and chemistry of the minerals they contain. The other field where mineralogy is very important is geochemistry. This is essentially the study of the chemistry of earth materials, which relates the collective chemistry of the minerals they contain. We also have a discipline called structural geology and tectonics, where the deformation of rocks is essentially controlled by the orientation of crystal structure of its constituent minerals here. We also have a subdiscipline environmental geology and hydrogeology, where we study how the biosphere, hydrosphere and atmosphere interacts with rocks and minerals. Essentially, the lithosphere, how it interacts with this biosphere, hydrosphere and atmosphere. So, finally, we have also a branch called economic geology, where we study the origin and beneficiation of mineral deposits here. So, in each field, mineralogy or minerals that are present in rocks or in ore minerals, they are the most important parts in this particular field here. Now, let us see how the external form can be related to the internal structure here. So, I give you an example with fluoride, where I will show you that how the external form reflects the internal form here. So, I have already told you that minerals have a very definite orderly arrangement of atoms in well developed crystallographic sites here. So, you see the external form in this crystal here. This is a mineral in the isometric crystal system here, and what you see here. So, if you see, these are the unit cells or the building blocks of this mineral here. So, these building blocks, they are cubic in shape, they broadly define also the outer cubic shape of this mineral here. Now, we can also have how the internal structure also makes how the minerals look like externally. You see the crystal morphology, where the well developed crystal faces that we see in some examples I have tried to give you here. This is topaz, this is kyanite, this is pyrite and this is garnet, where each mineral has a different crystal habit here. Say kyanite, you see here, this is an elongated habit here, and in pyrite you see these are cubic shape here, and in natural garnet crystals this is a dodecahedron shaped mineral here. Okay. So, as I was telling you here, so one of the subfields of mineralogy is to study the physical properties of minerals. So, what are the physical properties of minerals we study? Because this is important, because when you go to the field and see rocks, you have to identify the rocks. So, how to identify? You have to identify the minerals, and how you will be able to identify the minerals? You will have to use certain properties of the minerals, and I have listed in this particular slide what are the most important physical properties. One is the hardness of the mineral, whether the minerals contain cleavage or whether there are fractures, and what is the luster of the mineral, and also what is the color, and what is the color of the mineral in powder state, what is its density, and also the crystal habit. Each mineral has different properties under this subheadings here. So, I give you an example about the hardness of the mineral, and this is one of the most important table that we use for the we ask our students to remember, and this is called Mohs hardness table here. And what you see here, and this table has been referenced from 1 to 10. Talc is the softest mineral, whereas diamond is the hardest mineral here. And also there are certain natural materials here which can be used to know where with respect to these minerals what is the hardness. So, for example, fingernail has a hardness of the order of around 2.5. So, if you want to identify gypsum which is softer than fingernail, so fingernail will scratch gypsum. So, this is an example that your fingernail is scratching gypsum here. So, this is the way we use several materials here. So, fingernail is one, brass, iron, pocket knife or metal file, all these of different hardness are used to find out within this grouping of this Morse hardness scale where a particular mineral is there, whether it is harder or softer than this particular materials that we are using here. Now, the other important aspects of minerals is that in gemstones here. So, these are very precious material and this is used in jewelry, and I am giving you some examples of minerals which are used in gemstone. So, one of the variety is called andradite variety of garnet with olive green to emerald green in color is called demantite. The blue corundum is called sapphire, red corundum is called ruby, and purple quartz is called amethyst, and green beryl is called emerald, and this is diamond here. So, this is a very important industry here where this naturally occurring minerals are used as gemstone here. Now, I will now give you two specific examples how minerals are extremely useful to know earth process here or earth's evolution here. Now, let us have a look here in this diagram here. So, earth is around the age of the earth is around 4,550 billion years old here. So, if we talk about that earth was formed here, now this is this entire period of time we have crossed and we have come back to this particular part here. And there the subdivision of this entire earth's history has been made into several subparts. The Hadean part is the first around 500 million years or 500 to 600 billion years of the earth's early history is called Hadean time, and then from around say 4,000 million years before present to 2,500 million years before present we call the Archean period here. And from 2500 to around 544 million years before present we call it Proterozoic, and from 544 million years before present to the present day we call it as Phanerozoic, and this has been subdivided into three parts called Paleozoic, Mesozoic and Cenozoic here. Now, if you see this part from 4,550 million years before present to 544 million years before present, this constitutes the Precambrian period here, and it constitutes nearly 87% of earth's evolutionary history. And one of the most important part here is that you do not have the fossil record in the rock record, we do not have body fossils here. So, it is very difficult to know this time division. So, how this is solved, that these subdivisions and whatever has happened in between, how do you know that? So, one of the minerals or several such minerals which has given some very important part of this evolutionary history of earth is some minerals called say zircon and monazite. So, I give you an example with a mineral called zircon. Say for example, its chemical composition is ZrSiO4, and this is essentially acts as a chronometer or it is used in a geochronology, and it acts as a timekeeper for Earth's evolutionary process. Particularly, this is extremely suited to date ancient and hot rocks here. Now, Simon Harley and Nigel Kelly, they published a paper in Elements, and they have given a very nice heading here, zircon, this is tiny, but timely. So, what is important here is that these are very tiny crystals in rocks where they occur here. They are around say 150 to 100 micron long, and they even in that particular small volume in which they occur, they have exceptional memory of the arts of the time when they are formed in rocks here. So, what are the basic principles on geochronology that we use and apply with zircon here? So, this is essentially we use the law of radioactivity, where the rate of decay of a radioactive parent atom is proportional to the number of parent atoms remaining at a given time. So, this is essentially this is rate, and if we use a proportionally constant, that is decay constant, and this is the number of parents that are present here, and this is negative sign, because with decay the concentration of the parent decreases here. So, if you write it the rate, that is rate of change of the parent with time d n dt, and if we integrate that, ultimately we come up with an equation where the daughter by parent, that ratio is equal to e to the power lambda t minus 1, where lambda is the decay constant here. So, if we can measure the daughter and parent ratio, and if we know the decay constant here, so theoretically it is possible to calculate the time the radiogenic clock when it started. So, the time elapsed since the radioactive decay start occurring in that particular mineral here. Now, zircon and monazite, they are single mineral chronometer, and they contain uranium and lead and also thorium, and these are the decay equations here. 238 uranium decays to 206 lead, 235 uranium 207 lead, and 232 thorium decays to 208 lead. So, what you can do here is that it is possible for you to measure the isotopic ratio and can determine the time here. So, I am giving you an example how zircon is used in rock record to find out the earliest history that is still recorded in earth. So, this is the map of Australia, and in the Western Australia there is a place called Jack Hills here, and in Jack Hills Earth's oldest dated material has been found, and there is a place called Eranondo Hill, and this is in Western Australia, and there zircon has been found in a rock. This is a quartz pebble conglomerate, and this is found in Mount Nadir gneiss terrain. So, in that conglomerate there are zircon crystals here. So, this is the sedimentary rock here, and people have separated these zircons here, and this group of people, this is Professor John Valley of Wisconsin Madison, and this is Professor Simon Wild from Curtin University, and this is Aaron Kovasi, is a student of Professor John Valley. They have found from these rocks zircons which are as old as 4.4 billion years old. So, you see here. So, if you want to measure, if you want to get that time, what you have to do here is that you have to measure the isotopic ratio in very high spatial resolution, and you require an instrument where there is a very high sensitivity and very high precision level of isotopic measurements here. You can measure uranium lead isotope ratios, you can also measure oxygen isotopes and also trace elements in zircon, and this is the machine which is called sensitive high resolution ion microprobe machine. So, this is from Australian National University, Canberra, Australia, and also this machine is also there in Curtin University and in many other places in the world. It is called ion microprobe machine, which allows measurement of this particular the zircon, the isotopic ratio in this kind of spatial resolution here. So, around 40 micron spatial resolution you can measure the isotopic ratio in the zircon crystal here. So, you see I have shown you 3 examples here, and this is the work that was done by Professor Simon Wild and his co-workers in 2001, and they have found out a spot where they have found out a date of around 4,404 million years old age that has been found here, and all these spots that have been found in that zircon crystal is all of the order of older than 4,000 million years. And this is you see the same zircon crystal. This is a CL image. These are also cathodoluminescent images here. And here they all have found out in some zircon crystals the dates which are very old. And you see here I have just summarized that if the earth was formed around 4,550 million years before present, the oldest date that has been found out here is 4,400 million years here. So, within 150 million years of earth's formation, the material that was formed, that is now preserved only as single crystal. The rock of that age is destroyed. That rock, there is no rock from say 4,550 to 4,000. There is some report of rock as old as around 4,000 million years or 4 GA old rocks are there, but the first 500 million years of history, that rock is not preserved, but the minerals which were formed, particularly this zircon, that has survived later processes here and can tell us, yes, there is evidence that there was in the earth, there was rock that was produced as old as 4.4 billion years. So, important thing that I have tried to emphasize here is that you have rocks, you have minerals, certain minerals have exceptional memory of time information. So, zircon is one which has that, and that is why it has been able to date different periods of magmatism and metamorphism and the time periods of division that we have in the geological time period, that is built up particularly for the Precambrian by dating zircon, and also there is another mineral which is equally very robust, that is monazite. This is a phosphate mineral here. Now, I give you another mineral whose significance is also there and is used as a recorder of orogenesis here. I think you will be able to appreciate this diagram or this image here. This is the alpine Himalayan mountain chain here, and this is essentially your alpine, this is the Himalayan mountain chain here, this is India here. And what you know here, that from your geography, or you must have known that where the India is now joined with Tibet now, or Tibetan plateau or the Eurasian continent. In Jurassic, India was not here. India in the Jurassic period was in the southern hemisphere, and then it started its northward journey here, and it ultimately collided with the Eurasian plate here. So, when it collided, before that what was there? You have Neotathian Ocean there. So, because that it was moving towards north, the Neotathian Ocean was consumed beneath the Eurasian plate by a process of subduction. So, this is oceanic crust is subducted below the continental lithosphere, and as more and more oceanic crust is subducted and is transported to great depth, and what happens here is that at some stages here it goes to a depth and then it is returned and it is ultimately exposed on the earth's surface as evidence of very high pressure metamorphic, high pressure low temperature metamorphic rocks here. Now, I give you an example that how closure of the Tethys and the rise of the Himalayas can be studied here. So, I am taking an example from the work carried out by Patrick O'Brien and their group, and that was published in Geology in 2001. So, this is a map from Khagan area in northwest Pakistan, where there is a rock that is exposed there called eclogite, and it is essentially a garnet, omphacite and rutile bearing rock here. Omphacite is a clinopyroxene here, and there are two places here where these eclogites are reported here, one in the Khagan and other in the Indian part is in near Somorari. These eclogites are exposed here. And what is the significance of eclogites? So, this is the metamorphic facies diagram here, where this is a binary pressure temperature diagram that has been shown here. And in this diagram you see here the different metamorphic facies fields are shown here. And where is the eclogite facies find? The eclogite facies are at a pressure above 12 kilowatt here. And you see here at 12 kilowatt. So, if you multiply with around say 3.5 5 kilometer depth. So, you see if you have to have eclogites, the rocks have to form at a depth of around say 45 to 50 kilometer depth. So, if the rock was once at the surface and if you this eclogite is now exposed on the earth surface, what you will find out, this has to be buried to that depth and it has to be transported to the earth's surface here. Now, in eclogite there are sometimes there is a mineral that is present, its name is quartzite. This is a polymorph of quartz crystal here, and this is from the same Khagan locality. They have reported this quartzite here within this mineral called omphacite. And you see here, this is a very rare mineral. Quartzite is a very rare mineral. And what happens? You must be seeing something interesting here, particularly if you see in here and here. So, around quartzite there are radial fractures that have been developed here. In the host omphacite there are radial fractures here. And what is important here, these two cases, the minerals are shown, you have a central part and there is an outer peripheral part here and remal part here. The central part is essentially quartzite and the outer part, this is no longer quartzite, this has been transformed into quartz. This between quartz and quartzite is the high pressure polymorph. So, this is the dense phase here. If this is an extremely dense phase, what it means that you have volume has to be very low here. So, when this quartzite bearing rock, I will show you shortly at what depth this quartzite bearing rock is formed. When it comes out, because ultimately this rock is now exposed on the earth's surface, that is why we can study them. So, when this is transported from that great depth to the present surface here, to the earth's surface here, what happens? That pressure is released here. So, that means there will be an expansion, volume expansion of this mineral here. So, because these are very compact host mineral, so omphacite or some case the garnet, they cannot expand. So, this is essentially this development of radial fractures are a manifestation of the exhumation of these very deep crustal rocks to the shallower depth. So, that this quartzite which tries to resist this tries to expand, but this has been resisted and this is the expression of this radial cracks that has been developed here. And what happens here is that people have experimentally studied the stability of quartz vis-a-vis quartzite here. So, you see this is the polymorphic transformation line here and at pressure. So, this is a pressure temperature diagram here. This pressure is in the gigapascal unit here and this is temperature in degree Celsius here, and in this part here this pressure has been converted into overburden pressure or depth. So, you see if you have to have a quartzite in your rock, what does it mean? It means that the rocks have to be buried to a depth in excess of say 100 kilometer. So, this is essentially the mantle depth here. So, if you have an eclogite where you have quartzite, if someone is able to find out quartzite, what it will tell us? It tells us the rock has to be transported to that depth and then it has to be exhumed here. So, how to transport? This has to be transported in a convergent plate boundary through a process of plate subduction here. And this people have modeled this using quartzite eclogites from Khagan and Somorari here. And this is one of the most fascinating parts of Earth's processes, the plate tectonics that we know now about, the subduction processes here. So, it is still an enigma how rocks, particularly continental crustal rocks, are buried to that depth, how rapid it is buried and what is the time scale which is taken to exhume this to the earth surface. So, that quartzite is not completely converted into quartz. So, with these two examples I finish this introductory lecture on mineralogy, where I tried to give you an overview how mineralogy is important in the overall study of geology here. So, in the next lecture I will discuss about the crystallography part. We will start with a symmetry of crystals here. Thank you.